All right, good morning. Um, I'm starting to talk about section 5.4 here and uh, sampling distributions in the central limit theorem. And it gets kind of a little bit wordy with some definitions here, but the big concept in this section is that in the previous sections, 5.1, 5.2, 5.3, we were talking about calculating percentages or probabilities uh, for individual data points when compared to a normal population or normal distribution. And in this section, what we're really going to be doing is talking about taking samples of data points and comparing the mean or the average of that sample to the population and calculating percentages that way. So we got lots of definitions here. Sampling distribution is a probability distribution of a sample statistic. In our case, we're going to be really talking about sample mean. So when we create a sampling distribution here, it's going to be of sample mean. And the general concept here is you have a large population and you want to do some kind of study on it. And you're going to take multiple samples across that population and calculate a mean from every single. You see all of these different samples here have an X bar. They all have their own individual sample mean. And what's interesting is that even if this population itself is not a normal distribution, when we take a number of samples from that population and create a distribution of their sample means, that distribution will be a normal symmetric distribution. So one of the interesting things that we utilize in section 4 is we can convert a non-normal population into a normal population by taking samples, multiple samples, instead of a single large sample. Some symbolism here. The first one we need to know is the mean of the sample mean. So if you took all of these samples and calculated a mean for each one, a sample mean for each one of these, and then averaged those, found the mean of all those sample means, the result would be equal to the population mean. Okay, so you're much more accurate to take multiple samples, get an average of each sample, and then average those averages than you are to take one large sample and get one single big sample mean. The second one we have here is called standard error of the mean. I don't like that they put that terminology after they explain what it is. But if you were to create a sampling distribution from all these sample means, and then you were to find the standard deviation of those, that's what this standard error of the mean is. And we've got a very simple equation that allows us to calculate this. The standard error of the mean, and again, both of these, because we're talking about values that are derived from or sample means that have been collected, use that little X bar symbol after them. This one's easy. They're equal. It's equal to the population mean. This one, a very simple equation. Take the standard deviation for the population divided by the square root of n. Remember, n is your sample size. Okay? I will tell you that while conceptually there's a fair amount different in this section than, let's say, section 5.2, mathematically speaking, this is the only difference. And all the formulas and everything we use, Google Sheets, Desmos, if you're using a TI-84, whatever it is, this is the only thing that changes. And all of those calculation tools are powerful enough that you don't have to do this calculation separate. You can just plug this directly in and it's going to give you the correct answer. Kind of zoomed in here because I want to do a split screen here and show this, what we're going to be working on over here. Example 1, I asked you to read through it. I didn't ask you to really try it yourself, one, because it's a little tedious. They literally take a data set, 1, 3, 5, 7, and they take sample size of 2 out of it. So 1 and 1, 1 and 3, 1 and 5, 1 and 7, and so on. And they calculate the mean of each one of those samples, just like this diagram up here. Each sample has its mean. If you add these 4 numbers up and find a mean, you're going to get 4. If you add all these numbers up and divide by 16, because there's 16 samples possible here, you're also going to get 4. The mean of these sample means is equal to the population mean. It actually works out. The other interesting thing is they actually calculate the probability of each one of these means happening. How many times does the mean of one occur? Once. How many times does the mean of two occur? Twice, and so on. And then they make a histogram out of it. And what do we see? We see that histogram of this distribution is a normal, what would look like a normal curve or a symmetric bell curve. So that's just further illustrating the idea that we can create a normal curve out of something that isn't a normal curve. Let's scroll down here and get to some examples. Interpreting the central limit theorem. This was a pretty simple question. They ask you to find random samples of 100 cell phone bills. Mean was 63, standard deviation was 11. So find the mean and standard error of the mean for the sampling distribution. In other words, they want you to find this mu x and sigma x bar. Sorry, mu x bar and sigma x bar. Well, this one's just equal. They told you the population mean was 63. That doesn't change. Standard deviation is now going to be divided by the square root of our sample size, which was 100 cell phone bills. So we take 11 divided by the square root of 100, which is 10. We get 1.1. Very simple calculation. Try yourself too. Just ask you to do the same thing. Interpreting this, here they're asking you to sketch a graph. This is the bottom line that you need to know. When you take a number and divide it by another whole number, the result gets smaller. The bigger this n, your sample size gets, the bigger the denominator of this fraction gets, the smaller the end result becomes. Standard deviation is the distance from your mean in the middle of your bell curve to your inflection point, the point where the curvature changes. When you divide here, you make this outcome smaller. Essentially what you do, and you can very quickly compare these two graphs, the mean is still in the middle of both of these graphs. But what has happened to the graph? It's compressed together in the middle. Okay, you've pulled that standard deviation, which was, I believe, 18, and changed it to 9. You've cut that inflection point distance down. So when you do this and you're using a sample instead of an individual data value, you're squeezing your distribution together and you're getting a tighter distribution. So keep that in mind. That's really what they want you to get out of example number 2 here, or example 3 here. The effect that this has on your normal distribution is to compress it and tighten it closer together. And here's where we get into actual probability. So this is the one I really want to go over. We'll read through this question. We'll do example 4. The graph on the right shows the length of time people spend driving each day. You randomly select 50 drivers, ages 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Assume that standard deviation of the population is 1.5. The first thing we want to look at here is we're looking at this age 15 to 19 group, and they have a mean driving time, an average driving time of 25 minutes a day. So that's our mean that we're going to work with here. Secondly, we have a 1.5 as our standard deviation, but we also know we're taking a sample of 50 drivers. We're comparing a sample of 50 drivers to the population, not an individual driver to the population. Okay? We're going to use the same normal distribution calculation that we did in earlier sections in this chapter. Okay? We know that it's an in-between question. We need to find the area in between two values. That means we need to find the area to the left of the larger value, 25.5, and the area to the left of the smaller value, 24.7, and then we're going to need to subtract those answers. So we're going to do that right here. We're going to do normal distribution, 25.5 as our x value, a mean of 25, which was given to us in the diagram, a standard deviation of 1.5 divided by SQRT, parenthesis, 50 is our sample size. Okay? And then the word true because we wanted to do a cumulative distribution. Now, I didn't put an equal sign in front of it because I want to leave this in here. We'll hop over here really quick. Here's a little tip for you. If you copy that, paste it into this cell, double click in there and just put an equal sign in front. And what did it not like? Nope, I know what it did. I wrote normal. I should have just wrote norm distribution. There we go. Let me go back in here and fix that. Sometimes I forget that and write normal. So there we go. Now, if we look here at the answer that the textbook got for this, they calculated a z-score of 2.36. They went to a table. They got a value of 0.9909. We got 0.990788893. Our number is actually much more accurate than the textbook number because they rounded right here to a 2-decimal z-score. All right, so let's do the second one, norm distribution. Okay, this time we're going 24.7, mean of 25, standard deviation 1.5 divided by SQRT of 50, comma, and the word true. Good. We'll copy that over to here. Put our equal sign in front. And we got 0.07864. The textbook got 0.0793. Again, much more accurate here. They're using a rounded z-score. Okay. And lastly, if we want to find the area between those two values, I'll type it in 25.5 and 24.7. We're just going to do the subtraction of those two cells. So it equals this number minus this number. 0.9121. They got 0.9116. There's a difference of 5 10,000. Guess what? Our number is actually better. So that's the very easy way you would do this. You can also use an inverse norm function, and just when you put in your standard deviation, you would put in 1.5 divided by the square root of whatever your sample size is. When you get to try it yourself for, they just change the sample size to 100. So you're literally doing the exact same things as this here. You're just dividing by 100, square root of 100 instead of square root of 50. Mathematically speaking, that's the only calculation difference in anything we do in this section compared to the previous section. Okay, so keep that in mind. Do your best. Email me with questions, and thank you for listening.